All right, you're here recording in progress, so we'll go ahead and get started. All righty, so we are over here. Just make a quick few remarks about the test. So I've graded all the exams. You should have gotten an email back from me over the weekend sometime about your tests. 10 questions, 10 points each out of 100. And I also sent a solutions video. If you did not get an email back from me about your test, then let me know. Also, a reminder, please, when you send in your homework and your exam, have them in separate emails, okay? Because sometimes I miss one or the other. In other words, you submitted the test and I think, oh, you just did the test and not the email, and vice versa, not the homework rather. And if I checked that, oh, you did the homework, but I may have missed that you got the exam also. And remember, I don't look at the homework very carefully at all. It's pretty much just, I see that you did it, but obviously I don't have the time or energy to look at every single problem that you do. So for the homework, I just pretty much say, okay, you did it or you didn't do it, and that's about it. But the exam, of course, I have to look more carefully at. So please separate the emails for homework and tests. And that was part of the reason why some of you maybe got an email back from me about, hey, I didn't get your homework or I didn't get your test. And sometimes the reason, in fact, quite often the reason is because you sent them both in the same email. So I thought you only sent the homework and not the test, and vice versa. Okay, and in the email announcement clearly state, as most of you have been doing, but just in case, if you're submitting the homework, make sure it says, hey, this is the homework. And if you're submitting the test, make sure you know it's a test. So when I look at it, I say, oh yeah, you're submitting the homework or you're submitting the test, and so on. So please don't send them together. That will help me out a lot for that. Okay, I did not have to curve this exam, unlike the first exam. I think most people finish on time without any issue. Okay, so we've had 2 exams now. There are 3 to go. So we're done with this, we're done with this. So we're 40% done, I guess. The next exam covers some of chapters 8 and 9. Okay, so this is test 3, test 4, and our last test, which seems to be our biggest, and it is our biggest, as you can see. And keep in mind, my grading scale was 90, 80, 70, 60. So 90% an A, 80% is a B, 70% is a C, 60% is a D, under 60 is failing. And if you're off by 1%, then it switches to a minus or plus. So in other words, 90 is an A, 89 would be an A minus, 80 would be B, 79 would be a B minus, and so forth. And if you drop one more point after that, you get the plus grades. So that means 88 would be a B plus, 78 would be a 78 would be a C plus, and so on. Okay. So we are over here. Looks like 3 weeks for the next exam. Friday, the 15th of October, exam 3. And then we'll just move on after that. All right. So Friday's a quiz, Friday after that a quiz. We do have a flex day, school holiday on Wednesday the 13th, just be aware of that. It's a flex day, teachers have to meet and do stuff, but you don't have to. Okay. All right, so we're on 8.1, 8.2, 9.1, 2, and 3. Okay, so any quick questions before I go on? You can either unmute yourself or put it in the chat, otherwise I'll go ahead and get started. All right, I hear nothing and see nothing, so we'll start. Okay, 8.1 is on arc length. Arc length. A little bit of theory, not much, but some. Okay, so here's a function. Suppose I wanted the arc length from point A to point B, right? So if I were to walk in a curve pattern, right? Walk along this curve, like so, how far did I walk? If I walk in a curve pattern. So the usual trick that we do in calculus on page 544 is we can take the region and chop it up into tiny little pieces. Okay, so here's our curve. If I just go straight from the beginning point to the end point, well, that doesn't look like a good approximation. Okay, then they split into 2 pieces and 3 pieces and 4 pieces. Okay, notice if I chop this up into 4 pieces and just go straight line from there to there, there to there, there to there, okay, it looks like a better and better approximation. Okay. And as you might anticipate, the usual game is let n approach infinity, the number of pieces that you chop up into approaches infinity. So delta x gets really, really small. The approximation gets better and better and better, so much so that you would say, okay, if I just go along the straight line segment for delta x being very small, I get a really good approximation of the arc length, right? And by analogy, if you could take a, let's say spaghetti, okay, a piece of spaghetti noodles or something that's all curved, right? Okay. But if you were to chop it real finely, chop, 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 and just take one of those little chops, think, oh yeah, it's a straight, it's straight. And you would say that for all of them, right? If you chop it real finely, okay, so you've got some curved looking, spaghetti thing. I don't know, just make up anything. Goes like that. So it's not straight. Okay, but if you chop, 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 right, all the way through, take any one of those little pieces and you say, oh yeah, it's straight. Okay, and you just add them up for all of them. Okay, so here's a typical piece of what's happening. So the interval from A to B, I want to find the arc length from A to B. Here they chopped it up into n pieces, delta x. Okay, so I decided to go along this straight line segment and this one and this one. And it's a fairly good approximation. We know it's not exact, but if you slice it thinner and thinner, the approximation gets better and better and better, right? Well, can I find the distance along here? Well, yes, it looks like it's a hypotenuse of a right triangle, right? If I go straight over here and straight over here, I can get a right triangle. This would be delta x, and this would be delta y. Would that be? Okay. That's what this is. The length is the limit as n approaches infinity. N means chop it up into n pieces. Okay. And the distance from p sub I minus 1 to p sub I, you're just finding all these distances. So I'm really just adding up the lengths of all these hypotenuses. That's a hypotenuse, that's a hypotenuse, that's a hypotenuse, and so on. Okay. Well, the distance for any of these is square root of delta x squared plus delta y squared, right? Delta x, delta y, hypotenuse. A squared plus b squared equals c squared. So delta x squared plus delta y squared is equal to hypotenuse squared, or the hypotenuse is the square root of delta x squared plus delta y squared. Okay, now, how do I find delta y? Well, we can figure out the slope of this thing. Right, slope is delta y over delta x. Okay. Ignore the subscripts for now. Delta y is f prime of x sub I star delta x. Don't worry about the stars. I'm not going to emphasize it that much, but if you just take any one particular piece, okay, delta y over delta x is approximately f prime of x slope. So delta y sub I is f prime of x sub I star delta x. So if I take this expression and plug it in here, it now looks like this. In case you're wondering, don't take notes on this. Okay, and I'm not testing on any of this. I'm just giving you the derivation of where the formula comes from. So delta y sub I, they replace it with this. Then you can factor out a delta x here, you may notice, delta x squared. Okay, you can factor out a delta x squared. If you take it outside of the radical, it becomes delta x. Inside, you have radical 1 plus f prime of x sub I star. Okay? And that's what you have in the limit. Okay, so as usual, what happens in calculus, you take the limit as n approaches infinity. Okay, delta x gets smaller and smaller, and the integral becomes from a to b radical 1 plus f prime of x squared dx. Or you can say dy dx squared dx. Okay, so bottom line, that was a quick rundown of why the formula works. I could just give you the formula, but I'm obligated to show you where it comes from. You're not responsible for this. You might say to yourself, I have absolutely no idea what you did. That's okay. Okay, all you need to do is use the formula. Okay, but some of you might be interested. Instead of I just give you the formula, here's the formula, use it. Okay, somebody might say, how did you come up with that? This is where it comes from. It's a quickie version. I just went through it kind of rapidly, but at least you can say, okay, my calc teacher showed me why it worked and how it worked. And there it is. So what do you need for the test is really all you care about. And put this on your next cheat sheet. It's on page 545. So either this or this, I think I would prefer to use this one. It's a little bit clumsy to write f prime of x bracket squared. Okay, so I'll be writing this in general. Arc length is the integral from a to b of the square root of 1 plus dy dx squared dx. And there's good reason for writing it this way too, is in case we have x as a function of y. All right, so if you have y as a function of x, arc length is the integral from a to b of the square root of 1 plus dy dx squared dx. Okay, put this in your next cheat sheet. So you're given a function, and why does it work? That was my 2 cents of derivation of why it works. Okay. And if you say, I don't understand anything about what you said about derivation, that's okay, just be able to use this. So you find a derivative, square it, add 1, take the square root of the whole thing. That's what you're integrating. Okay, so it's pretty straightforward. And I'll hasten to add, we also have x as a function of y sometimes. It's very simple change. How do you think this would change if you have x as a function of y? Well, instead of saying dy dx, we would say dx dy squared, and then on the outside it would be dy. You just have a role reversal, just have x and y interchange, as it were. Okay. I mean, I don't think you have to write that on your formula sheet if you don't want to, but if you want to, you may, but it should not be that big a deal. You just look at it and say, oh, they have x as a function of y. Then instead of dy dx, I'll make it dx dy squared, and then this becomes a dy. And we'll see examples of that also. Okay. Okay, so bottom line, what do you need to know, right? You don't need to know this derivation. Maybe some of you got it, understood it. But if you have absolutely no conception of what I just did, that's okay. To find arc length, use this guy. Okay. All right. Yeah, here we are. On page 546. In my opinion, you don't have to put this on your cheat sheet. This is just x as a function of y. So instead of dy dx, it's dx dy squared dy. You integrate with respect to y. Okay. So it's up to you. Do you want to put that on your cheat sheet or not? Of course, everything you put extra on your cheat sheet, that's less room for other stuff. So, you know, I don't think you really need it. Just make the simple change from, you know, just put this one down. And then if you see x as a function of y, you should be able to say to yourself, oh yeah, just change that to dx dy, and that's a dy. Okay. All right, something else I want to mention quickly is, please notice this form of raising something to the 3/2 power. That raising to the 3/2 power is going to show up in quite a few problems. Notice the way that they write. This gets a little confusing. Just say 13 to the 3/2. The normal way to write 13 to the 3/2 is 13 radical 13. Okay, that's simpler than raising something to 3/2. As you might anticipate, raising to the 3/2 happens a lot here. There's a very good reason for it, because this is a square root, right? Square root means you raise something to the 1/2. If you integrate something to the 1/2, you end up with a 3/2 power. So a lot of these problems, you have an answer raised to the 3/2. This is the proper style for writing it. So let's say 13 to the 3/2, 13 radical 13. So if you have x to the 3/2, x radical x. Okay, logic is 13 is like 13 to the first power, right? This is 13 to the 1/2. So that gives me 13 to the 1.5 or 13 to the 3/2. Okay, I'll show you that when we get more problems with that. But this section, there's a lot of blah, blah, blah raised to the 3/2. This is the proper way to write it. Okay, so I think we have something like 19 to the 3/2. All right, 19 radical 19. So W to the 3/2, W radical W. You don't have to write down what I'm saying now. I don't plan to, because you'll see enough examples of this. That's the proper way to write it. This is considered simplified. And if you don't agree with me on that, just think of, you know, the general population. The general population, not necessarily math people, but just ask random people on the street, right? If you showed them something to the 3/2 power, or if you showed them that, much more people would understand this, right? Say, oh yeah, I think I remember something about square root 13 times the square root of 13. but fewer people would understand, I don't remember what is raising something to 3 has power, right? In terms of simplifying. Okay, so let's get started with some of the problems. Okay, so 8.1, what was the homework? 1, 2, and 9 to 21 odd. Okay, here we go. Page 548. So for the benefit of those of you who don't have the book and aren't getting it, there's 1, there's 2, and then on this side, that, and that, and what else do we need? We just have to go up to 21. And yeah, there we go. Okay. And actually, I was just looking at something. 8.1, 21 has a graphing calculator icon, which means I don't want it. Okay, so I'm going to change the assignment. Anytime you see this picture in the text, it means it should be done by a graphing calculator, which means it's not easy to be done by standard means. Okay, so 21 should not be done. So 8.1, let me get rid of the last one. So cross off 21. Let's just make it 9 to 19 odd. Okay, so please make that change. Let's make 19 the last one. Okay. All right, so here we go. I did my own strange variation. The integral is from a to b of the hypotenuse dx squared plus dy squared. If you divide inside the radical by dx squared and multiply outside by dx, you get the same thing, right? And you don't have to take notes on this if you don't want to, but here's another way of thinking about it. Okay, this represents the hypotenuse. The little change in x squared plus little change in y squared is equal to the square of the hypotenuse. So what's the difference between dx and delta x? Not much, except dx is really, really, really small. dy is really, really, really small in theory. Okay. So this is valid. I'm multiplying by dx over dx squared inside. And this is 1. Dx squared over dx squared is 1. And dy squared over dx squared, you can write as dy dx squared. Anyway, this is the arc length formula. Put it on your cheat sheet. Okay, and now I'm ready to try problem number 2 for you. Use the arc length formula to find the length of the curve y equals radical 2 minus x squared. X goes from 0 to 1. Check your answer by noting that the curve is part of a circle. Okay. So what does that mean? Okay, so here's the function. A little bit of algebra, you get x squared plus y squared equals 2. Right? Square both sides, add x squared, looks like that. That's a circle centered at the origin with a radius of square root of 2. You told me to go from 0 to 1, 0 to 1. Plug in 1, you get 1. So the point on the circle is 1, 1, which means you have a 45-degree angle. Okay, so the arc length should be 1/8 of the circumference of the circle, right? Circumference of the circle is 2 pi r, right? This is 1/8 of the circle, going from 0 to 1. So this piece here, that's 1/8 of the whole. So I just take 1/8 of 2 pi r, 2 times pi times the radius, which is radical 2, pi radical 2 over 4. So I'm anticipating the answer to be pi radical 2 over 4. So I actually just finished the easy part, the second part of the question. The second part says check by noting that the arc is a part of a circle. So I did that part. Now for the actual integration part. All right, so y equals radical 2 minus x squared. I can write it as 2 minus x squared to the half. So what is dy dx? 1/2, 2 minus x squared to the negative 1/2. times negative 2x by the chain rule. 2's cancel out. A little bit of algebra. Negative x over radical 2 minus x squared. Okay, now I need dy dx squared. Notice a couple of nice things about this. When I square this expression, the negative changes to positive, and I get to get rid of the square root, right? So the square of this thing is x squared over 2 minus x squared. This is dy dx. This is dy dx squared. Now I'm supposed to add 1. So 1 plus this thing. Well, I got this weird thing in the denominator, so I'm going to choose to write 1 in the form of 2 minus x squared over 2 minus x squared, right? Do you agree that this is still 1? 2 minus x squared, 2 minus x squared. And you said, what did you write it like that for? Because I need a common denominator. So here's 1 plus dy dx squared. And then I notice on the top, the x squareds cancel out, such as of 2 over 2 minus x squared. This is the thing that I have to integrate under the radical. So I'm integrating square root of 1 plus dy dx squared. So first I figured out 1 plus dy dx squared. Here it is. So I take the integral of the square root of this mess. All right, so integral from 0 to 1 of 2 over 2 minus x squared. Okay, the trick for this is divide top and bottom by 2. See how I divided by 2, divided by 2. 2 over 2 is 1. Square root of 1 is 1. This becomes 1 minus x squared over 2. I can write as x over radical 2 quantity squared, right? Notice if you square this thing back out, you get x squared over 2. See, it now looks like 1 over square root of 1 minus something squared. That's my arc sine, you might remember, inverse sine. Okay, so I want this to be u. So u equals x over radical 2. I snuck in a 1. So the coefficient is 1 over radical 2. Du is 1 over radical 2 dx. So in order for me to substitute, I need a 1 over radical 2 inside and a radical 2 outside. And I change the limits. Okay, plug in x is 0. U is 0 divided by radical 2, which is 0. Plug in 1. If x is 1, u is 1 over radical 2, which is the same as radical 2 over 2. So my new integral is going to go from 0 to radical 2 over 2. All right, so I is radical 2 is in front. New integral is from 0 to radical 2 over 2 of this stuff. 1 over radical 2 dx is my du over square root of 1 minus, and now by substitution, this is now 1 minus u squared. Du over radical 1 minus u squared. This, you might recall, is my inverse sine. This is inverse sine. The derivative inverse sine of u was 1 over radical 1 minus u squared. Therefore, the integral of 1 over radical 1 minus u squared is inverse sine of u. Okay, look that up, or you can put it on your next cheat sheet if you wish. Right, this inverse sine from 0 to radical 2 over 2. Radical 2 is in front. Inverse sine of radical 2 over 2 minus inverse sine or arc sine of 0. Arc sine of 0 is 0. Arc sine of radical 2 over 2 is pi over 4, because the sine of pi over 4 is radical 2 over 2. Okay, and remember, inverse sine picks a number between negative pi over 2 and positive pi over 2. So pi over 4. And get rid of that. Pi radical 2 over 4 is my solution. And I do notice it is the same thing as I got right over here. So it looks like we're good. Okay. All right, so that's that. Okay, then I did that. I'll let you do problem number 1 on your own. Then find the exact length of the curve, starting with problem 9. So we get some of those. Okay, 1 plus 6, x to the 3 halves, x between 0 and 1. By the way, in general, you don't have to graph these if you don't want to. All right, so what's dy dx? Derivative of 1 is 0. Derivative of this, 3/2 times 6 is 9, x to the 1/2, 9 radical x. Then I have to square it. dy dx squared, that's easy. If you square this, you have 81x. Add 1. All right, so this is what I want. I want the integral from 0 to 1 of radical 1 plus 81x dx, which of course means 1 plus 81x to the 1/2 power. Okay, I can do a u substitution if I wanted to, but again, it's easier in this case to just think of the chain rule in reverse. You can do that when constants are involved, but not with variables. Okay, if I were to differentiate this by the chain rule, when I got to this stage, what would I multiply by? 81, right, by the chain rule. All right, so if I differentiate, multiply by 81. Therefore, when I integrate, divide by 81 or multiply by 1 over 81. So I'm going to go 1 plus 81x raised to the 3/2. So there's that 3/2 that shows up a lot in these kind of problems. Divided by 3/2, which means multiplied by 2/3. And then by the chain rule, there's an 81 in the bottom. So here we go. 1 plus 81x to the 3/2 divided by 3/2 means times 2/3. And then by the chain rule, divide by 81. Okay. It might actually be easier to think of double checking this by differentiation. What's the derivative of this mess? Okay, 3/2 comes down, knocks out the 2/3, right? So that's gone. 1 plus 81x to the 1/2 power. And then by the chain rule times 81, that cancels that 81. So it works. All right, so this is 2 over 243. Plug in 1, 82 to the 3/2. Plug in 0. Careful when you plug in 0, you don't get 0 here, but you do get 1 to the 3/2, which is still 1. All right, here's what we're talking about. I want you to write the answer in the following fashion. So if you don't, I can take off points for it. Okay. So the best way to write something to the 3/2, which is what's going to happen a lot in this section. And it's no surprise as to why it happens a lot, because the thing that you're integrating is the square root, which means blah, blah, blah to the 1/2 power. If you integrate something to the 1/2, there's a 3/2. So a lot of these are like that. Okay, so how do I write 82 to the 3/2? 82 radical 82. So I want you to get used to writing something to the 3/2 power. Now, don't leave your answer to the 3/2 in general. Write it like this: 82 radical 82. And the logic is this is 82 to the first power. This is 82 to the 1/2. 1 plus 1/2 is 1.5 or 3/2. Okay, this is considered simplified. Okay. Again, you can think of the definition of simplified if you ask the general population, not math students like you, but just anybody out in the street. Are they more likely to understand this or to understand this? Right? Well, many more people would understand this. They might not understand everything about it, right? And say, oh yeah, I remember something about a square root and multiplied by 82. Sure, I know what that means. But a lot fewer remember, what does that mean? If they ever had it at all. Okay. All right, problem 11, I think that's 11. Yes, it is. The reason why I wrote it originally as 9 is because I think it was 9 in the previous edition, and Mr. Stewart, the author, just moved it over to 11. So big deal. Okay, I'm not going to do this in its entirety. I'll just get to a certain part and then let you take it from there. There's something very unusual that happens to this kind of a problem. Okay, so 1/3 x cubed plus 1/4 x to the negative 1. That's the same thing as the original, right? And Mr. Stewart, the author, has some problems like this. I guess he likes this concept. So what is the derivative? So 3 now to the 1/3 x squared minus 1/4 x to the negative 2. Now, by rule, I'm supposed to square it. That seems like it'd be a big mess, but let's see what happens. If you square this, x squared minus 1/4 x to the negative 2 squared. Okay, squaring this gives me x to the 4th. That's easy. This one's a little harder, but that's going to be 1/16 x to the negative 4. How about the middle term, the 2ab term, right? 2ab, 2 times that times that. 2 times that times that. What happens when you multiply x to the 2 by x to the negative 2? X to the 0, which is 1. So I just have 2 times negative 1/4 or negative 1/2. All right, so one more time, the middle term, the 2ab term. Okay, a squared is that, b squared is that. In between is minus 2ab, minus 2 times that times that. Well, that times that is 1. X to the 2 times x to the negative 2 is x to the 0, which is 1. 2 times x to the 4th is negative 1/2. Now, here's the clever thing that comes out of this. By rule, I'm supposed to add 1. What happens when you add 1 to all of this? The only thing that happens is that the negative 1/2 changes to plus 1/2, doesn't it? And when I do that, very conveniently, it factors back. I mean, the algebra is the same as this. This is sort of an application of a squared minus 2ab plus b squared. This is a squared plus 2ab plus b squared. So this factors back into x squared plus 1/4 x to the negative 2 squared. In other words, if you were to square this back out, get that. And as you can tell, that's going to be nice because I'm going to have a square root of a square. So when you have a square root of a square, they just knock each other out. Okay, so one more time. I found dy dx, squared it, came out to be this. Add 1. If you add 1, the negative 1/2 just becomes a plus 1/2. The algebra is completely identical, then you factor it right back into the same thing as this was, except instead of a minus, it's a plus. So x squared plus 1/4 x to the negative 2 squared. So I take the square root of this mess, and the square root of this mess, you just lose that too. All right, so you just have x squared plus 1/4 x to the negative 2, which I would just say, etc. after a certain amount of time. So that's x cubed over 3 plus 1/4 x to the negative 1 over negative 1. Remember, you don't need a plus c for definite integrals. Clean this up. 1/3 x cubed minus 1 over 4x from 1 to 2. And I'll just say, etc. You guys can finish the rest of that on your own. Okay. All right. Then let's see. The last one I was going to show you today, about 15 more minutes. Okay, so we'll probably end early. Is problem 13. Let me take a look at 13 here in the book. Yeah. It used to be 11 in the previous edition, but it's now 13. X is a function of y. 1/3 radical y, y minus 3, y between 1 and 9. So all that's happening is a role reversal between x and y. Instead of y is a function of x, and x goes from blah, blah, blah to blah, blah, blah. You have x is a function of y, which would pass the horizontal line test, right? And y goes from blah, blah, blah to blah, blah, blah. So it's just a role reversal. So instead of dy dx squared dx, right? What do we say? It's going to be dx dy squared dy. Okay. When you can see, you could just as easily make it y as a function of x, and x goes from whatever, you get the same answer. You're just changing the roles of x and y. Okay. So if I distribute this, this is y to the 1/2 times y to the 1. So 1/3 y to the 3/2, right? And then 1/3 times negative 3 is negative 1. So I have negative radical y. y to the 1/2. So dx dy, that even sounds strange because we're used to saying dy dx, but dx dy is perfectly fine. So 3/2 times 1/3 is 1/2 y to the 1/2 minus 1/2 y to the negative 1/2. And then a recurring theme from Mr. Stewart, if you square this expression, okay, so what is this thing squared? 1/4 y. Remember, if you square this, y to the 1/2 squared, 1/2 times 2 is 1. Or you can say to yourself, okay, this means square root, right? Y to the 1/2 means square root. So if you have a square root and then you square it, just like y. Likewise, for this last expression, the b squared term, if you square it, 1/2 squared is 1/4. Y to the negative 1/2 squared, you multiply the exponents, y to the negative 1. And then similar theme as problem 11, the middle term, 2ab, 2 times that times that. Well, 2 times 1/2 is 1, times 1/2 is 1/2. So what happened to the y's? They cancel out. Same reason as the previous problem. Y to the 1/2 times y to the negative 1/2 is y to the 0, which is 1. And a recurring theme, if you add 1 to this expression, right, you get 1 minus 1/2, which is positive 1/2. So 1 plus dx dy squared is 1/4 y. You pretty much just copy this, change the minus to a plus. 1/4 y plus 1/2 plus 1/4 y to negative 1, and then refactorize it back. And you might look at this and say, I don't know how to factor that. You don't really have to, just peek at what you had over here and just change the minus to a plus. 1/2 y to the 1/2 plus 1/2 y to the negative 1/2 quantity squared. And if you want to convince yourself of that, actually square that out. Square this out, and you'll get this thing back. And again, that's nice. So if you have a square underneath the square root by formula, then the square root and the square just cancel each other out. So square root of 1 plus dx dy squared means square root of this guy, square root of a square. Well, if you have a square root of a square, just drop the square root and the square. So you're just integrating from 1 to 9, 1/2 y to the 1/2 plus 1/2 y to the negative 1/2 dy, and I'll just say etc. This problem's far from being done, but at least the integration is straightforward. The rest is just some heavy duty algebra, plugging stuff in, and that's that. Okay. Right, so that's enough of what I was going to do today. I was going to do some more tomorrow, but I think that's good enough for now. So main thing for your next cheat sheet is put this thing down and be ready to do problems like that. All right, folks, I'm done for the day. Let me stop the share, check if there's anything in the chat. And if not, then I'll just let you go. Okay, I don't see anything now. So any questions, please? Otherwise, we're done for the day. All right, I just see a thumbs up, and that's about it. All right, folks, have a good day, and we'll see you next time. Okay, all right, bye, everybody.
Thank you, Professor.
Thank you. Bye.